Hello, my name is Skuse, and today I'm presenting my long term about the effects of light frequency and intensity on the eye dilation. So, as a little bit of background on what my long term is about, whenever you first walk into a dark room from, say, a lit hallway, it's very hard to see what is happening in the room or what even is in the room until your eye dilates to the light level that's in the room. So it depends on the light level in the room compared to what light level you were in the hallway, that it will take different amount of times for your eyes to vary. If it's a little bit of change, it's almost instantaneous on your eyes dilating because there's not much of difference that it has to go through. The smaller the pupil of your eye, the less light that gets in. This is better for a brighter environment because you don't want to go blind. The larger your pupil, however, the more light it lets in because in order to see a darker environment, your eye needs to have more light enter it so you're able to see everything in the room. So you may be thinking, what on earth, how would I test this? So in order to do this, I'm using different frequencies and intensities of light and seeing what is the best way for your eyes to adjust from a regular lighting, so say a bright hallway, to the dark, say a room that has no lights on. In order to do this, I use different colored LEDs that have different wavelengths associated with them because they're different colors. And by varying the voltage that was going through each LED, I was able to have different intensities of light. And so what the purpose of this is looking for the best solution from the problem of transitioning to light to dark. So there was two separate things that I was testing. The first was the immediate visibility, and the second is the lasting visibility. This basically means that the immediate visibility is how long it would take you immediately from going into the room to be able to transition to a darker surroundings. The lasting visibility is once you are now in that surroundings and your eyes have somewhat dilated, are you able to have no lights on and to be able to see anything? So my two claims are a compromise of being able to see immediately and lasting will be the best. So a yellow or green will perform the best out of the colored LEDs because these are in the middle of what I'm testing. I'm testing a red, orange, yellow, green, blue, and white light in my long term. However, I believe that blue will perform the best immediately because it is a higher intensity, higher frequency light, so it has more energy with it, but red is a lower energy. However, it is sort of a easier or darker on the eye so that it would be easier for in the long run for somebody to see. And also increasing the intensity of the light will decrease the time it takes in order for your eye to dilate to a darkness in an inverse squared fashion. The reason I'm claiming this is due to the circular nature of light, and the area of a circle is a squared function. So the setup for this is I had a few different items that I was using. The first was an adjustable DC power supply. This is what was providing the electricity for the LEDs that I was using, in addition for the ability for me to change the voltage that I was using as well. I also had to use a voltmeter in order to measure the voltage that I was using for each LED. I used a desk lamp to dilate my eyes to a, say, hallway brightness level, various colored LEDs, which were shown in the last slide, in order to get different colors from them and for my eye to dilate to. Identifiable shapes. I'll get into what these were used for later. However, originally I was using words, which was very hard for me to identify in the long run, so I moved to shapes, which are much easier to identify. I used 3 shapes: triangles, circles, and squares, which are all easily identifiable from one another. In addition, I used a timer in order to test how long it took for me to identify what one of these shapes were. And finally, a low light environment that the LED would be one of the only lights available. So whenever I was using the LEDs, I had 3 separate levels that I was testing them with in order to change the intensity of them for different amounts of light to enter my eye. So the 3 levels that I used, I just called low, medium, and high. So the low, as you can see from the pictures on the right, is a barely lit light bulb. You can see there's not much light that's giving off. Medium, it's about halfway between a high and a low. Again, that is the second photo. And a high, so that's one of the brightest levels that the LED can be. And you can see this graph at the bottom, which shows a linear relationship between these voltages, so that I can say that the medium is about halfway between low and high. So here you can see my setup. On the left, you can see the universal power supply that I was using. You can see the knob on it, which is what I was using to adjust the voltages. Sitting on top of that is the voltmeter that I was using in order to measure the voltage that I was using for each light bulb and set it correctly each time I was doing it. In the middle, this is where you have the main box. Inside of it, you can easily see the identifiable shapes. You'll be able to see a video later of me going through this process. On top of it, underneath that blanket, you can see a small circle that is the LED that I was using. And on the right, you can see a desk lamp. This is what I was dilating my eyes to, and then turning it off and moving to the LED. So the whole process for the short-term testing, I followed a series of steps. The first was to turn on the power supply so that the LED would be powered. And then I would change the voltage on it to the appropriate voltage that I was using, say for red, 1.8 volts. I would then adjust my eyes to the lamp light, so this is the simulating a bright hallway. And then I would turn off the lamp and start the time on my timer. This is to simulate entering a dark room from the bright hallway. Then I would look at the shape that was inside of the box that you saw on the last slide, and then once I had identified that shape, I would record the time that I was at, and then write it down. I would repeat this 4 times for each LED light level. So say for red, since I had 3 of them, I did it 4 times for the low, 4 times for the medium, and 4 times for the high. I would then average those together to get set times for each one. I would repeat this for each LED that I had. So here is a video example of what I was doing. So you can see here I'm adjusting my eyes to the desk light. It takes about 5-10 seconds to do that. And in the middle of the screen, you can see the LED. This is the part where I'm adjusting my eyes to the light level that is happening here in order to identify the shape that is in the middle. You may have noticed that the LED was changing intensity, however, it wasn't. This was just the camera focusing in on the light level that was available. Here is the data that I collected. This is the first part of it, with red, orange, and yellow respectively. As you can see, I have each of their individual voltages listed, like red from 1.7 to 2, and orange and yellow along with that. You can see the times I recorded for each one. So for instance, on 1.7 volts for red, it took about 44.48 seconds the first time I did it. Then the rightmost column, you can see the averages. This is the average of all the 4 trials that I did for each voltage of each light. So for instance, for red, it goes from around 45 to 34 seconds. You may notice these ones are in the 45 to 34 range, which is fairly high for the rest of them. Orange is in the 31 to 8 range, which is a lot lower than what the red was. You may notice between the 1.8 volts and 2.1 volts that there is a significant drop. I was not expecting this, however, it did occur between these voltages. For yellow, it had a similar pattern to the higher voltages for orange, sitting at around 14.7 to 4 seconds that it took. So overall, just in the first 3 lights, I was able to see a drastic difference between the lowest intensity for red and the highest intensity for yellow. For green, I tested from 2.5 volts to 3.5 volts. As you can see on the right-hand side, the averages for this consisted anywhere between 24.3 to 16.3. Although this was a higher voltage than what yellow had, the times, as you may notice, were higher overall. For blue, I did something a little bit different because it had a little bit of a wider range than the other lights did, so I tested 4 intensities instead of 3. These ranged anywhere from 2.5 to 3.5, and their averages ranged from 16.31 to 1.18. As you can see, there is a pretty drastic jump between 2.5 and 2.8. However, based off what the orange, it wasn't all that unsurprising at this point. However, getting down to 1.18 seconds, I thought was fairly good for what the LED had. Finally, the white light, these voltages I used it for was around what I used for green and the lower end of blue. However, it performed similarly to what blue did, with its lowest voltage having around a 13.6 seconds on average, and the highest voltage used for it at a 1.83 seconds. So here's my first graph that I have. On here, I have labeled I have put every single data point that I collected and color coded it. As you can see, there are groups of colors for each one, with the darkest color being the lowest intensity and the brightest color being the highest intensity. For instance, if you look in the middle of the graph, there is 4 points there, 4 clusters. On the leftmost one and the highest one is the lowest intensity of red, the one to the right of it is the medium intensity of red, and the one to the right of that is the highest intensity of red. Underneath the middle one is a dark orange, that is the lowest intensity of orange, etc. Something to point out here is that the red sort of lines up with the green and the orange sort of lines up with the blue. These are complementary colors, and they kind of line up with each other's patterns, which I thought was interesting to point out. However, by far, we do see that the blue and white perform the best out of all of the colors. However, yellow and orange aren't bad in their own rights. Here on this graph is just the averages, so it might be a little bit cleaner and easier for you to see where these data points are, and as a result, be able to see that the blue and white do perform better. So now moving on to the second part of my testing, which is moving from the dark environment with, say, a light on that your eye is dilating to turning off that light to be in complete darkness. So the first parts of this followed similarly to the last step. So the first step was to turn on your power supply so that your LED was powered, and then check your voltmeter to make sure that you are at the right level. Turn off your desk lamp so that your eye is dilating to the light that is above what you have. And then after that, you cover your LED to be in complete darkness and you start your time for this section. You then identify your new shape, and then whenever you have done that, you stop your time. You repeat this for each intensity of the LED, similarly 4 trials for each one, and then you do it for each light. Here's an example of that. As you can see, I'm adjusting my LED at this point. I turn off my desk lamp to dilate my eyes with the LED that is on top. As you can see, I've just covered it to dilate my eyes to the complete darkness. You may see the light on the left that is coming from the power supply. That didn't affect me at all because that was covered by the blanket and I was not able to see it. By this time, I had identified the shape and I turned the lights back on and recorded my time. Here's the data from this section. Anything that you see a 0 for is something I couldn't really tell the difference between the LED that I was using in complete darkness. Whenever I was switching between the two, I was still able to see the shape and my eyes did not have to dilate very much in order for this to happen. As a result, the time was unrecordable and I counted it as a 0. However, for the 2 volts on red, I was able to have a difference between the LED and complete darkness, end up with around 4.42 seconds on average. For orange, I had the same thing happen for 1.8 volts where I wasn't able to tell a difference in terms of lighting, so that again was counted as a 0. For the other 2 oranges though, they did have a time at 3.8 and 7.3 seconds-ish. Yellow, however, didn't have any of those 0 seconds, and all of them had times ranging from 4.6 to 7.9 seconds. Green, similarly to the red and orange, again had its lowest voltage. There wasn't much of a difference, so it was recorded as a 0. The 3 volts for green and 3.5 volts for green did also both have readings for me at 3.1 and 5.24 seconds. Blue, again, I tested with the 4 separate voltages, and they all had time associated with them, ranging from 3.7 seconds to 9.1 seconds. White also had readings for all of its voltages, ranging from 3.6 seconds to 7.62 seconds. And here's the data associated with that. You can see there are the points at the bottom, like I mentioned, that are at 0 because there wasn't much of a difference for me, and then all of the rest of the points. You can see that in terms of times of identification, red, the low orange, and the low green performed the best because there wasn't much of a difference, and the blue and white performed probably the worst. However, it wasn't as bad of a transition as from the original light to the LED lighting. So on this graph, this is just the averages of all of those. However, on this graph, this is a combination of the previous graphs. This is going from the light to LED and the LED to the darkness. This is combining their averages since there was no two trials that could directly link together. As you can see, red performs the worst out of all of them, sitting around 37 to 46 seconds overall, which isn't terribly good, unlike what I originally thought. Orange is moving in next with its lowest at around 32 seconds overall, and then green follows that and then going on, it moves down to orange, yellow, and the blues, where you can see at 3 volts, the middle intensity, white, is performing the best. Now I wanted to see how energy efficient each of these options were. In order to do this, I used the equation for electrical power, P equals IV, where P is power, I is current, and V is voltage. I then transformed it where energy over time is power, so I was able to get the equation energy per time equals current times voltage, and transform that to get an equation for energy, where energy equals current times voltage times time. Using this, I used an ammeter that I was able to connect to my system that I had and turn it to the appropriate voltage with a LED hooked up to it, and get a current reading for each intensity of each light. In addition, since I had times recorded previously for going from the light to the LED, I was able to use this energy equation to calculate the energy that each LED used. And here's that data. So here's the first set, where red was fairly low in its energy usage, everything being under 1 joule of energy used. Orange, similarly, everything was under 1 joule of use, ranging from 0.1 joules to 0.569 joules. Yellow, along the same lines but a little bit higher, also had 0.268 to 0.74 joules being used. For green, blue, and white, we see our first energy usage as above a joule, with green operating at around 1.233 joules to 4.114 joules. However, with blue, we immediately see a drop back down to 0.059 joules to 0.127 joules, which are all fairly efficient. White, we again see 0.044, ranging to 0.162. All these options don't use very much energy, however, green is by far the worst because it's the only one that reached above a single joule. Here we can see a graph where all of our results are plotted that we just shown. It's pretty obvious to see that green is by far the worst performer in form of energy efficiency, which made me potentially wonder that there was something wrong with the green LED. However, due to me only having one of them, I was not able to tell if there really was, or if that was just the way that green actually is. And if you notice that the second lowest intensity of blue does perform the best out of all of them in terms of energy efficiency. So to wrap this up, the blue and white LEDs are the best to use in almost every situation that I tested. The only thing that I found that they were a little bit slow for was the LED to darkness transition. However, it didn't perform as bad as some of the other ones overall. Yellow and orange are good alternatives to these. They perform moderately on each set of them, and like I said, green did not perform that well. And the results do indicate to me that there could be a relationship between complementary colors and their receptors in the eyes. Like I noted earlier, the red and green paired together nicely on their graph, and the orange and blue also paired together, which could potentially mean that there is a relationship between these in terms of eye dilation. For future testing, there was a few things that I wanted to test, however, I didn't have the ability to test when I was going through this. For instance, having an exact low, middle, and high for each light that would be exact in terms of fluorescence would be a lot more helpful in terms of getting a linear relationship between them. However, I wasn't able to do this. And finally, have multiple versions of each light, like I noted earlier, to see if there was any manufactured defect. This was especially prevalent in the green, which I thought could potentially have problems with it, but like I said, I was not able to test this due to me only having one. That is all I have for my presentations. If you have any questions, feel free to email me at coleskuse@freedomarea.org. Thank you for your time.